And the healthcare provider or a patient has to enter, the inputs are baseline characteristics like the stage of a disease, and then the post-treatment measures of PSA. So they all get entered. And then the website does its thing and comes up with a quantitative prediction about the future. And so here's a mock example, and we'll have some, when we go to the website, we'll see more of this sort of thing. So a patient was treated in 2003, localized prostate cancer, radiation therapy. They had various pre-treatment characteristics. So this PSA pre-treatment, so that's moderately high, T-stage, Gleason grade, that's what it looks like under a microscope. Certain dose of radiation they were got delivered, and we're now sitting in 2010, and up to now they haven't had any clinical recurrence. So that's 7-8 years. That's good. Remember, they do have this series of PSA values, so you'll see this pattern. It goes down, got to 1.1, and then it's starting to creep back up again. So that's sort of not terribly good news. Maybe anxious patient here. So then we're saying, given that information and today's date, what's the probability of a cancer coming back within 3 years of today clinically? And so what the scheme here is, we've got a whole bunch of data of patients like this. We've built some models. We've learned something from that data. We're going to plug in what we've learned from the training data with this new data I just showed you for this one patient. Churn the handle in the model, and it comes up and says 22%. Probability of prostate cancer clinical recurrence within 3 years, 22%. And so that's the goal, and that's sort of the end of it as far as what I'm going to show here, or what we're going to do with it. So that's sort of just talking about what the next steps might be. So 22% is depending on your risk level or how you view that, or if you understand 22%, you might take some actions, and you could. That seems to me it's quite high actually, but probably you'd intervene with salvage hormone therapy. So that's standard therapy, blocks testosterone production, has some side effects. You'd be worried. You don't want to take that lightly if you don't need to. So the idea is, if this probability is high enough, maybe you embark on this hormone therapy. Or maybe you say, well, it's looking a little high, and I had a PSA annual test plan, but let's do another one in 6 months. So get a sort of an updated assessment. So there's sort of decisions to make, or you could do nothing. So this talk's going to be about how do we get 22%, and hopefully I've got time, how do we validate and show that the model is valid. So there's going to be some formulas now. So I go to many medical talks with things I don't understand at all. So if you don't like formulas, just think about me when I see medical talks and slides and x-rays and things like that. I took most out from them, but not all of them. So there's data here. So this is going to be about building the models. So there's data, there's baseline values, T-stage on the patients. There's follow-up information, T, whether they recurred, and then delta is sort of an indication of whether they recurred or not. And then there's PSA data, longitudinal PSA data, so that's Y. So in this setting, recurrence and PSA are, after the treatment, they're both responses. We have to think about sort of models or equations for both those responses. And they're linked. PSA and recurrence are linked. So if the patient in my training data has a recurrence, delta will be 1. And if they're just been followed for 7 years and no recurrence, delta will be 0. So it's the indicator of recurrence. So I'm going to build models both for PSA and for recurrence, and they're going to be linked. So there's going to be a longitudinal model for the PSA patterns, and it's going to have random effects, which are sort of allows different patterns for different people. And then there's going to be a model for the time to recurrence as it depends on that pattern of PSA. So that's going to be a time-dependent proportional hazards model, or sort of a time-dependent Cox model. And you can fit those models and get the usual sort of parameter estimates, hazard ratios and stuff. I'm not interested in those. I'm just going to be interested in using these models for prediction purposes for an individual patient. So here's the type of data we've got. This is come about after working with various people and clinical colleagues who have colleagues at other institutions, and we worked with them to get the various data sets. So I'm from Michigan, and there's most of these patient series are just all patients we saw in the last 15 years at our institution who were treated with radiation therapy. So we've got a few thousand patients here generally, and I've split it up into a training data set and a testing data set. And to give you an idea of a PSA data, there's lots of this data. About every 6 months, all these patients have observations. So there's lots of PSA data with about 10 years of follow-up. And for the endpoint, the recurrence data, as I said, not that many people get recurrence. So only 15% of the people get recurrence in these data sets. So it's not that common. And so of the people who don't get recurrence, some died of other causes, and some are just at the end of a follow-up period. And there's a complication which is I'm not going to go into, but many of these patients actually got hormone therapy before they got the recurrence, so that has to be taken care of. And sort of another talk how to do that. Okay, so more pictures. So these are line plots of about 20 people. Again, log of PSA on the vertical, time since radiation therapy on the horizontal. Each line is a patient's pattern of PSA. And the top left is people who went on to get recurrence. So at the end of their line, more or less, is when each of those patients got recurrence. And so you'll see some structure and some heterogeneity too. Everybody comes down, basically, and then they go up at different rates. So that's sort of characteristic of recurrence. On the right-hand side are people who haven't had a clinical recurrence, still in follow-up. So they also came down, but they basically stayed down. So this is the majority of the patients. And then group C are people who opted for or were given hormone therapy, salvage hormone therapy before the recurrence. And so they also have this increasing pattern, and that was the reason they got hormone therapy, because PSA was going up. So that's sort of a typical data. And so the model is going to think about patterns of PSA, and there's going to be heterogeneity between individuals, and things like T-stage and the like are going to impact that pattern or expected pattern. And then the clinical recurrence is going to depend on, so the rate of recurrence at any instant is going to be a function of the PSA value, how fast PSA is going up there, and the baseline variables. So I'm going to show you, this is a picture of a longitudinal model, and I'll get to the equations in a second. So this is sort of the assumed shape of PSA pattern for everybody. So here's a line here. So what you get to observe is this line plus a bit of noise added on for each patient. And the features are, this initial drop and then a sort of linear line on this is a log scale. And so what tumors grow vaguely exponentially, so linear on a log scale makes a lot of sense here. And what is different is each patient can have their own starting level, their own amount of drop, and their own rate of increase. So with that flexibility, you can fit the sort of data we saw before. And also these levels and drops and rates of increase can depend on the pre-treatment characteristics. So that's sort of the essence of a model in words. And I could explain every single equation here, but I probably won't. But this is sort of a mathematical form. Log of PSA has some true value plus noise. The true value has a starting point, a drop, and a linear increase. Putting those together, and the little subscript I means they vary from one patient to the next. So it's a random effect model. We allow for sort of outliers can be accounted for, and there's a mean structure depending on the baseline characteristics too. So that's sort of a standard random effect model. So then there's a hazard model. So this is the event happening, the recurrence happening. And this is a Cox type model, and so the terms here, you don't need to go through too much of the details, but it depends. Instantaneous failure rate for getting recurrence at any time. This says it depends on the PSA, it depends on the slope of PSA, depends on the pre-treatment values, and here's an adjustment to take account of people who got salvage hormone therapy. So this is sort of a model which is the style of this model is quite common in statistics. And the most important feature here was the slope of PSA. That was the driver, the most important determinant of the recurrence rate. Okay, so that's the model, and it's a complicated model, and and this isn't something you can go to Stata or SAS or something and fit. You have to write code, and this is what graduate students are for. And and it is. In my case, it definitely is. And it took about 18 months to get this to really run properly. There's a lot of tender loving care needed to get these things. So if you're thinking your lab tech can go and do this in a couple of days, it's not going to happen. So there's different aspects to this model, and there's the things we were just talking about, those phi's and omegas. Those are sort of population parameters. And then, as I said, each person has 3 determinants: starting point, a drop, and a rate of increase. So those are called Ri. So all these parameters are saved, and they're going to be saved. And when I go to a website, we're just going to call on these set of saved things and incorporate those. So when we get a new patient come in, we don't have to refit this model, which is a good job because it took many, many hours to converge. But we've saved the output from the training data. And we want to predict future PSA values, and so that's relatively easy because we have an equation for what PSA would be, and we can just extrapolate that into the future. And so I've saved the starting point, the drop, and the rate of change for each person. And it's lots and lots of things saved. I can predict for everybody what's going to happen in the future for them. So we have this way of predicting PSA, and we have saved for each person their own set of determinants of starting point. So we have lots of those saved, and they're all sort of plausible. We have a whole range of values saved for each person. They're all plausible, and so we have sort of plausible patterns for PSA. So this is sort of trying to take account of the uncertainty. So if I go to just a couple ahead, this is a prediction for a person who entered the data, which is the red pluses. So I don't know, 6 or 7 data points, and then where this green line is the today. And so the blue shaded region is sort of a range of where PSA might be in the future. So that's what, to get PSA, but that's sort of an intermediary. What we really want is the clinical recurrence. So this is probably the most technical part. So we're being what's called Bayesian here. So we're actually going to integrate out the parameters so we can get, so this is just the first equation. I'll try and walk you through it. The probability of recurrence within the next A units of time, given you've made it to today. So given you've made it today, it means T bigger than today, and the PSA and the baseline variables. So this is sort of a residual time. What's the chance, given you've made it today with your data, of something happening in the next A units of time? And we can express that as a sum over saved random effects. And those formulas, conditional on the random effects, require some integration of this hazard function, and this has to be done numerically. And so it's messy computationally, but it's doable. Okay, so I have a mechanism, algebraic mechanism for getting the probability of the event within any unit of time. So we showed that one. So if this is a person whose PSA is going up really rather fast, so for that person you'd expect the probability of recurrence to be quite high. And so this graph, this line here, shows from today out to 3 years the probability